All right, let's talk about one-to-one functions and their inverses. So first, let's review a little bit. Do you recall which relations are functions? And in order for a relation to be a function, it has to pass the vertical line test, which means any vertical line passes through the relation only once. So this one is in fact a function. But this vertical line touches this one in 3 places. So this is a relation. And this one is obviously a relation. By the way, this is a special function. It kind of looks like a heart, so it's actually called a cardioid. But it is a relation. All right, let's talk about inverse functions. So suppose we have this simple function. When x is 3, f of x is 5. When x is 7, f of x is 9. When x is 10, f of x is 13. Well, the inverse function in simplest terms simply reverses the input and the output. So if your input is 5, for the inverse function, the output will be 3. If I input 7, what do you think the output will be? I mean, if I input 9, the output will be 7. And if the input is 13, what do you think the output will be? If you guessed 10, you guessed correctly. The notation for an inverse function is f to the minus 1 of x, which in exponential functions, that would be a reciprocal, but you definitely don't want to confuse a reciprocal with an inverse. How do you find the inverse algebraically? Well, first we can write y for f of x. And when we find the inverse, we're basically just switching the x and the y. So that's our next step. We're basically going to switch x and y. And then simply solve for y. So we add 5 to both sides. Divide both sides by 3. And that's our inverse function. So you'd say f inverse is x plus 5 over 3. All right, if f and f inverse are the inverse of each other, then if you compose the functions, you get your original x back. So f of f inverse is x, and f inverse of f equals x. You can use this rule to check and see if two functions are in fact the inverse of each other. Let's try one. So the question is g of x the inverse of f of x? And you could try this one on your own. All right, so it doesn't matter which one is the inside and which one is the outside function, but if you compose them, you should get x. So let's just try g of f of x. So wherever you see x, we're going to put f of x. So that's 3 times x plus 5 over 3 minus 5. 3 divided by 3 is equal to 1. So g of f of x is equal to x. So that means that g of x is in fact the inverse of f of x, or vice versa. F is the inverse of g. They're the inverse of each other. Let's find an inverse from the graph. All right, given this graph of f of x, can you draw its inverse on the same axes? And if you want to go ahead and try, this would be a good place to hit the pause button. All right, so a good place to start might be to identify a few points on f of x. So on f, we have -5, -1. So what point will be on f inverse? If you guessed -1, -5, you would be correct. So if you haven't already finished the problem, I would stop here and fill in these two tables using these points shown. All right, so we have -4, 0 here. So that means that 0, -4 is on the inverse. -1, -1, -1, 1 is on the original function. So that means 1, -1 is on the inverse function. 2, 3 is on the original function. So 3, 2 will be on the inverse function. And then 3, 5 is on the original function. So 5, 3 will be on the inverse function. All right, so we can start by plotting those points. When x is -1, y will be -5. When x is 0, y is -4. When x is 1, y is -1. When x is 3, y will be 2. When x is 5, y will be 3. And the only points that won't flip when you're graphing an inverse would be the points where y is equal to x. And in fact, if you placed a mirror there, the graph would be a mirror image across a mirror placed at the line y equals x. So this part of the graph would look like this. And this part of the graph would look like this. So this is your f inverse. Let's try another. All right, given the graph of f, can you draw f inverse on the same axes? So if I were you, I would hit the pause button, fill out the table, and then try to draw the inverse function. All right, so we could start by labeling a few points. So -4, -2. That's -5. We have -3, 0, -1, comma 3, and the point 4, 4. So points on the inverse function would be -2, -5, 0, -3, 3, -1, and 4, 4. And this makes sense. We switch the x and the y, and since the x and the y are equal, they won't move. And in fact, the point 4, 4 lies on the line y equals x. And if you wanted to, you could draw that line to sort of help you. So you can think of the line y equals x as the mirror that the graph is reflected over. So the point 4, 4 is going to be the same on both functions. And then -2, -5 will be on the inverse function. 0, -3 is on the inverse function. 3, -1, and 4, 4. So the graph of the inverse function will look roughly like this. All right, let's talk about another example. All right, in order for a function to have an inverse for its whole domain, that function must be 1-to-1. So far we've been doing 1-to-1 functions. So the inverse of this one, we would just switch the x and y. And this is a 1-to-1 function because the inverse is in fact a function. Let's do a counterexample. All right, this function is not a 1-to-1 function. And let's try and take its inverse and you can see what goes wrong. So you would just switch the x and the y. Oops, sorry. And you can see that this is not a function because sometimes 7 is 2 and sometimes 7 is 4. So the inverse is not a function. You could, however, find the inverse if you restrict the domain. So if we just try to find the inverse of this part of the function, then the inverse would be a function. So we just cut this part off. Let me write that down. It's probably easier to see when you look at the graph. So let's look at our function f of x equals x squared. We tried to draw the inverse function. You could put your mirror at y equals x and reflect this, take the reflection across y equals x. So this part, it's reflected here. And this fails the vertical line test. So the inverse is not a function. So in order for f of x equals x squared to have an inverse, you would have to restrict the domain. So if we just took the part of the graph where x is greater than or equal to 0 and found the inverse, then the inverse is a function. You could also restrict the domain to x negative. And then the inverse will also be a function. All right, you can tell if a function is one-to-one just by looking at its graph. So to find whether something was a function, we use the vertical line test. So this is a function, but for it to be one-to-one, it would also have to pass a horizontal line test. So this is a function, but it's not one-to-one. So it does not have an inverse for all of x. This is a function because it passes the vertical line test. And it's a one-to-one function because it also passes the horizontal line test. This is a function because it passes the vertical line test, but it is not a one-to-one function because it does not pass the horizontal line test. So it does not have an inverse for all of x. You would have to restrict the domain for the inverse to be a function. All right, let's find some inverses algebraically. All right, let's let f of x equals x cubed. Can you find the inverse function? So if you remember from earlier, you could go ahead and try it. So we just switch x and y. And then solve for y. And because y is an odd root, you do not get plus or minus. That only happens when you take an even root. So f inverse is the cube root of x. Let's try another. All right, let f of x equals x over x plus x minus 1. And if I were you, I would hit pause to try to find the inverse function. So we switch x and y, and then we're going to solve for y. So multiply both sides by y minus 1. And then distribute. Sorry. And distribute. And then we want to get all of the y on one side and all of the x on the other side. So subtract y from both sides and add x to both sides. Then I can factor out a y. And then divide both sides by x minus 1. And you might have noticed something strange. And it turns out that this function is its own inverse. there's a few functions like that. All right, let's try another. All right, this one's very similar, so if I would definitely try this one on your own. So we switch the x and y. Multiply both sides by y plus 2. Distribute. Collect all the y's on the same side. Get all the x's on the same side. Factor out the y. And divide both sides by x minus 1. And that's your inverse function. Of course, minus 1 times x minus 1 is 1 minus x. So just to clean it up, I'm going to factor out a negative 1. But either one is perfectly fine. All right, let's try just one more time. And I would definitely do this one on your own now that we've practiced. All right. So we put the y where you see f of x. Switch x and y. Multiply both sides by y plus 2. And distribute the x. Get all the y on the same side. Factor out the y. And if you wanted to make it pretty, you could factor out negative 1. And there you go.